This lecture is going to deal with acid-base structure and also introduce the concept of pH. So we'll start off with a little demo, and we're going to ask ourselves the question of what do we expect to conduct electricity? And so what we have over here are a few samples: water, sodium chloride, HCl, CH3COOH, and NH3. And we can ask ourselves which of these would conduct electricity. You may recall previously that pure water does not conduct, but sodium chloride will conduct. And the point of that was sodium chloride has ions in it, and it's the flow of ions from one electrode to the other that completes the circuit and allows electricity to be conducted. So what we can do is now we can ask ourselves, HCl, CH3COOH, and NH3, will these conduct electricity? And so here we have in our video, we can start to see, here's our light bulb. You can see when I connect the light bulb with the piece of metal, it conducts. In pure water, nothing happens. If I move it to a solution of, here we have a conduction, and so that is CH3COOH. Water does not conduct. We put in HCl, we can see HCl conducts. And so now notice the difference here, HCl versus CH3COOH. We have a difference in that light bulb and the intensity of that light bulb. And finally, we can come over and we can say, well, what about NH3? Will this conduct? And so we can look at NH3, put the light bulb in, and yes, in fact, it does. But again, notice the difference in the light bulb. There's something different there about those two, giving rise to the difference in the brightness of the bulb. And what we're seeing here is the first thing we might think about is, based on our knowledge so far, these are all covalently bonded molecules. So they should not break into ions in solution, and yet we very clearly see the formation of ions. So what is happening here is we are starting to study our acid-base chemistry. We started talking about this last lecture. We're going to go into more detail now. And it's important to understand that acids and bases are everywhere. So most fruit that we eat is acidic. A lot of cleaners are basic. A lot of juices and seltzer water, things like that, are acidic. So acids and bases are all around us. The earliest definition of an acid and base is what's known as the Arrhenius acid and Arrhenius base. And this comes from a definition that it says an acid is a substance that dissociates to form H plus in solution. So something that's going to put H plus into a solution. One important characteristics of an acid that's helpful to know is acids taste sour. So anytime you're eating something that's sour, it is acidic. One other important thing to know is this H plus is often referred to as a proton, and that's because if you think about a hydrogen atom, it's a nucleus with one proton, no neutrons, and one electron. So if you remove the electron and you become H plus, all that's left is a proton. So chemists will use the word proton to refer to H plus a lot of the time. A base is then a substance that will dissociate to form hydroxide in solution. So now notice the definition of acid puts H plus in solution, base puts hydroxide in solution. Now bases often taste bitter and feel slippery. So if you ever get a cleaning solution on your hands and it feels slippery, that's a characteristic that it is a basic solution. Now the definition of acid-base that we started to study already is what's known as the Bronsted-Lowry acid-base definition. And this is a more general definition. And in this case, we're talking about movement of a proton. So a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. All right, so we can look at a reaction with the simplest acid-base reaction. H plus OH minus goes to water. So this is accepting a proton. This is giving up a proton. And so that's our acid and that's our base. Or we can think about it in terms of HCl plus water goes to hydronium and chloride. And so here we have showing in red, this proton ends up bonded to the oxygen. And one of the things that's important to know is it's this lone pair of electrons on water that's going to come out and take that proton. These electrons go back, and you can see this bond here came from these electrons. Right? And so in this case, HCl is our acid, it's donating a proton. Water's the base, it's accepting a proton. And what we're forming in the solution is hydronium. And one of the things that's important to know is the more hydronium in solution, the more acidic that solution is. So when we talk about how acidic something is, it's really a measure of how much hydronium is in solution. Now, what's important for us is to understand, to be able to identify what is an acid and what is a base. And so if you recall, the two major classes of acids we talked about, the first one had to do with where hydrogen is bonded to something highly electronegative. So what do we mean by that? Something like some hydrogen bonded to a halogen, or maybe a group 16 element. And the reason for that is the more electronegative this atom is, the more polar this bond becomes. And the more polar it becomes, the more it starts to look like A minus H plus and being an ionic bond. Now it's not an ionic bond, but we start to get closer and closer. And the closer we are to this extreme of an ionic bond, the easier it is to break this bond and have the proton leave and for that to be acidic. And so we can start to consider the strength of an acid. And so if we think about four molecules, CH4, NH3, H2O, and HF, and think about what's happening, these are all, so carbon, nitrogen, oxygen, and fluorine are all second period atoms. So we're going across the periodic table, carbon, nitrogen, oxygen, fluorine, and they have only hydrogens bound to them. And then we can think about ranking the acidity of these molecules, which is the most acidic and which is the least acidic. And when we think about that, it turns out that for these molecules, HF is the most acidic and CH4 is the least acidic. And in fact, the acid strength increases in this direction as shown. So HF is most, CH4 is the least. And what we're seeing is the more acidic something is, the more electronegative that element is, right? There's a direct correlation there. And that's actually the cause of the acidity in this case. So this is, again, one of our periodic trends. We talked about them in chapter 3. And so now we're seeing another one, acid strength. As you go left to right across the periodic table, acid strength increases because electronegativity increases, which is going to weaken the bond to that hydrogen. We can also go down a group. So we went across left to right on the periodic table. So let's go down the group and look at HF, HCl, HBr, HI. So now our halogens are going lower on the periodic table, and we can start to see which of these is the most acidic. And before we get to that, we can ask ourselves, what's different about these molecules? And one of the things I hope you recall from chapter 3 is what's different is the size. So as we go down a group, the size gets bigger of these halogens. And when we look at acid strength, it turns out that HI is the most acidic and HF is the least acidic. So acid strength is increasing as you go from HF to HI. And so going down a group, it's the size that matters. The bigger the element, the stronger the acid. And that really, the reason for that is, I like to give the example of if you have something like HF, you think about how that's going to bond. If here's my proton and here's my F minus, these two atoms are about the same size, and the bond that's going to be formed between them is the overlap of those atoms. If you have something like HI, your proton's still about the same size, but I is huge, right? It becomes much, much bigger. And so it's much harder to have good overlap of the orbitals to share those electrons. So the bigger the size difference between two things, the weaker the bond. And that's what we're seeing in this periodic trend here. So that was our first class of acids. The second class of acids are what we called oxoacids. And the key with the oxoacids was this group here, if you remember. So an element with a double bonded oxygen, and then an OH. And anytime you see this group, this proton is acidic. All right. And so an example of that here would be nitric acid. So you have nitrogen, double bonded oxygen, OH. That would be acidic. When we think about our oxoacids, we could compare to something like ethanol, right, which is a very similar molecule, CH3, CH2, OH versus CH3, C double bond O, OH. But this molecule, this proton, is not acidic. And the reason it's not acidic is we do not have this double bonded oxygen because this carbon is just bonded to two protons, two hydrogens. This is not an acidic hydrogen, while this one is because of the C double bond O. So we can look at another trend here of our oxoacids. So imagine comparing the strength of these molecules, which all contain the same OH group, right? So same OH group, and all we're doing is we're adding, in this case it's a chloride, and then we have an oxo group, a C double bond O, and then we have two of them, and then we have three of them. And what's the most acidic? And it turns out the most acidic is the perchloric acid. So the more of these oxygens on your atom, the more acidic it's going to be. And why is that? Well, we can use the simple electronegativity argument to say all of these oxygens are just pulling electron density away from this central atom, which pulls it from this oxygen, which pulls it from hydrogen. And so the more electron density away from this bond, the more acidic that bond is going to be. So just a couple quick notes on bases. We touched on these before, but just to remember, base is a proton acceptor. The more hydroxide in solution, the more basic that solution is. We have two major classes of bases. The first is a metal hydroxide, an ionic compound that's going to put hydroxide in solution. So if we have a metal hydroxide, that's going to dissolve in water to some extent, putting hydroxide in solution, and therefore making it basic. We can also have ammonia, or things that look like ammonia. So ammonia is NH3. So anytime you have a nitrogen with a lone pair and 1, 2, 3 bonds to it, that's going to be basic. This nitrogen has the ability to grab a proton to form something that's going to look like ammonium and therefore be basic. Now, one quick note, as you work through your acid-base chapter and as you study acid-base further, we can look at two reactions here. And the first one is HA dissociates to H plus and A minus. And the second one is HA plus water goes to hydronium plus A minus. One of the things I want to point out to everybody is these two reactions are exactly the same. Because HA here is in an aqueous environment, it's assumed there's water everywhere. And H plus aqueous is really the same thing as H3O plus. So in water, this does not actually exist on its own. It exists as hydronium, but oftentimes you'll see these written both ways. I will try to always write this way for everybody, but you might see it the other way. All right, so let's go back to this light bulb we started this lecture with. Now, remember we said we looked at two things. We looked at HCl, and this is acetic acid, CH3COOH. And one of the things we noticed is there was a big difference in the brightness. So HCl gave a very, very bright light bulb, and CH3COOH gave a very dim light bulb. So that tells us something. It tells us something about the amount of ions present. There must be more ions in the HCl solution than the acetic acid solution. Now, if these are both 0.1 molar in acid, what's happening here? Why are we getting more ions with HCl than we do with acetic acid? And the reason for that is a difference between what's known as a strong acid and a weak acid. So HCl is what's known as a strong acid. And a strong acid means we have 100% dissociation to form hydronium. In other words, however much acid we have here ends up as hydronium. This reaction goes only in one direction, and everything that started as a reactant ends up as a product. So if we start with 0.1 molar acid, we end up with 0.1 molar hydronium. And as we'll see in a second, that gives us a pH of 1. And we'll talk about pH in a second. In the second example, acetic acid is what's known as a weak acid. This means we have less than 100% dissociation. So what that means is, while we started with 0.1 molar of our acetic acid, only a small amount of it ends up as hydronium. Most of it doesn't react, it stays on this side. Another way of saying this is we have a two-way reaction arrow. This reaction actually goes in both directions. So some reactants go to product, but the products actually react and go back to reactants. So in this case, it turns out if we start with 0.1 molar acid, we end up with 0.0013 molar hydronium. And so if we look at the pH, and we'll talk about pH again, the pH is 2.87. Right, so a much, very different concentration of our hydronium for the strong and the weak acid. And so the stronger the acid, the more hydronium formed in a reaction with water, or the further to the right the reaction proceeds. And so that brings us to this pH scale. You may have studied pH before, but we just want to touch upon it here because it is such an important concept in chemistry. And the pH scale, right? So acidity or basicity of a solution is based on the concentration, right? H3O plus in brackets, the molarity of hydronium present. All right, so because concentrations can vary a lot, people use a logarithmic scale. And so the pH of a solution, and that is a lowercase p, capital H, is equal to the negative log of the concentration of hydronium. And anytime you see this p, lowercase p in an equation always just means negative log. So if you see that, it means negative log. Now, a lot of times we want to go in reverse. If you're given a pH, how do you find the hydronium? And I'll just show you this here if you want to go in the opposite direction. So if you're given the pH and we want to find hydronium, what we would do is move the negative sign to the left. And then to get rid of this log base 10, we do 10 raised to the exponent of negative pH equals our hydronium. And that comes from our log rules. I'm not going to ask you this for this course, how to do this. Next semester you would, but not for this course. But it is important to see how this is done. Now with the pH scale, a change in a single pH unit is a huge change in concentration because it is a log scale. And just to give you an idea of what we're seeing here, if we have a neutral solution that is equal concentration of hydronium to hydroxide, the pH is 7. If we are acidic, and acidic means we have more hydronium than hydroxide, the pH is less than 7. So the lower the number, the more acidic. And if the pH is greater than 7, it means we have more hydroxide than hydronium. And we can start to look up charts, just give it a sense of various pHs. Again, one of the things to take note of is your pH scale is on the right, and a single change in pH unit on this scale is an order of 10 magnitude. So every pH unit is a factor of 10 difference in concentration. And on the scale, we can look things up. So if you're interested, milk is slightly acidic, pure water is neutral, human blood is slightly basic, something like vinegar, lemon juice, very acidic, down by 2, black coffee, pH of 5, ammonia up by 12. And so a lot of things we use every day we can find on pH scales like this. It's also important to know there's a lot of good ways to measure pH. We can calculate it sometimes, but in the lab we can measure it. There's what's known as universal indicator, and this is a solution that'll change color based on the pH. And so you can put a couple drops of this solution into anything, and it'll change color, and based on the color, you can determine what the pH is. Or you can use an indicator, and an indicator is something that'll change pH only over a certain range. So a common one that people use is phenolphthalein down here, right? So this one is actually colorless until pH of just above 7, and then it turns pink and then goes to red. Right, so finally, there's a pH meter. These are expensive, but they do a great job. You can just stick it in solution, and in this case, it's going to directly tell you the pH through a measurement. So that gives you an overview of acid structure, acid strength, and a little bit about pH. Thank you.